Electromagnetism is a difficult subject. One of the reasons why it's so difficult is that it's very difficult to kind of make the leap, if you will, from seeing a demonstration of electromagnetism here on my desk to ultimately then spraying out various equations on the board. So because this process is difficult for a lot of people, physicists are very good at coming up with visual techniques, very simple ways, if you will, of visualizing what are ultimately difficult subjects, such as electromagnetism. The person most directly responsible for essentially starting this process was a man who lived in the 19th century named Michael Faraday. 19th century, that is the 1800s. Let me tell you a little bit about Michael Faraday. He was British. He, however, was very poorly educated. The reason why is that he came from a very humble background. Basically, his family was poor, so he had to leave school early in order to go to work and help essentially support his family. He actually took a job, however, at his local university, and when he took a job as a laboratory assistant, and he actually worked in the physics department there as a lab assistant, assisting professors in setting up demonstrations and experiments and so on. Luckily for Faraday, however, he was actually a genius. So even though his own formal education ended when he was in 6th grade, he essentially self-taught himself physics over the intervening years and essentially rose to prominence within the scientific community. However, because of his lack of formal education, he understood mathematics so poorly that he basically couldn't read the scientific papers of the physicists around him. So to compensate for this, he comes up with this mental scaffolding, if you will, this visualization of the electric force, and this is what is referred to as the field. Now, I'll be describing electric fields to you, but first let's begin with something that's a little bit more familiar. Let's begin with a gravitational field. Okay, so for example, let's say right here is the surface of the Earth. Okay, and then I take my marker in space, for example, and I place it near the surface of the Earth and let go of it. Force of gravity is exerted upon it, and it accelerates downwards. So let's say that the marker has a mass m, like so. I place it here in space and let go of it, and the force of gravity causes it to accelerate downwards. Okay, do the same thing at a different location. Take the marker and place it here, let go of it, and it does the same thing. Force of gravity is exerted upon it downwards, like so. So then therefore, if you recall from earlier in the first semester, the force of gravity that's exerted upon the marker is equal to its weight, mg. Notice I'm putting a vector sign here above g, acceleration due to gravity. Of course, that's straight downwards when you're near the surface of the Earth. Okay, now let's say that I wanted to talk about the Earth's gravity without bothering to have the marker itself present. In order to do so, what I'm going to do is take this simple expression and divide out by the mass of the marker to the other side of the expression. That is like so. And then this quantity right here, just g, of course, is acceleration due to gravity. But now a little bit more specifically, this is what is referred to as the gravitational field. And the gravitational field is measured not in terms of meters per second squared, as we did for acceleration, but it's instead in terms of newtons per kilogram. So, the gravitational field is essentially a visualization of the Earth's gravity without bothering to have to deal with the marker itself. So we just divide out by the mass of the marker. Visually, we represent the gravitational field as a series of vectors, as a series of field lines. The direction of these field lines corresponds to the direction that the net force of gravity would be exerted upon the marker. So for example, once again for the surface of the Earth. Okay, I can now represent the Earth's gravitational field as a series of vectors. In this case, the vectors point straight downwards, like so. So if I take the marker, for example, and I place it anywhere in space here near the surface of the Earth, the force of gravity is exerted upon it straight downwards like so. So the Earth's gravitational field, a representation of the Earth's gravity, is these series of field lines here which point straight downwards in the direction that the net force would be exerted upon the marker. Okay, now how many field lines are there? Well, technically speaking, there's an infinite number of them. So then therefore, what are the rules that we employ for drawing, for example, the field lines? There are 4 rules. Okay, so rules for drawing field lines. Okay, the first rule, very simply, is that the lines do not cross. And the reason for that is as follows. So for example, imagine that I took this field line right here, and I drew it instead like this. And then right here at this point, the field lines intersect each other. If I put the marker and I then place it right here at this intersection, what this would then mean is that there are 2 net forces exerted upon the marker. There's no such thing. Remember that the net force is the sum of all the forces. There can only be 1 net force. So then therefore, for that reason, the lines do not cross each other. Okay, the lines, once again, are a representation of the net force of gravity exerted upon the marker due to the Earth. Like so. Okay, and then the second rule is that we draw the lines symmetrically. Okay, you'll see why that is as I illustrate various types of fields for different types of electric charge configurations in a little while. But it's actually the last 2 rules that are the most important. Okay, third, the number of lines drawn is indicative of the amount of mass that's causing the gravitational field. The amount of lines drawn is indicative of the amount of mass that causes the gravitational field. So compare this diagram here showing the field lines associated near the surface of the Earth. How would the diagram look if instead we were talking about the surface of the moon? All right, so for example, let's say that this right here is the surface of the moon. Oops, surface of the moon. Okay, the moon's gravitational field is about 1/6 the value of the Earth's gravitational field, in this case when you're at the surface of the moon. So how would I then draw the field lines for the surface of the moon to show that it's weaker, for example, that is the magnitude of its gravitational field is weaker than that of the Earth? Well, I'm just going to draw less lines. So if I draw 4 lines, for example, on the diagram above for the Earth, in this case, let's say I just draw 2 lines. Like so. So when you compare the 2 diagrams, this immediately tells you that the mass of the moon is less than the mass of the Earth because its gravitational field is weaker. Okay, and then fourth. Okay, the density or the spacing of the field lines is indicative of the magnitude of the gravitational field. Okay, so what does that then mean, for example, in the context of my diagram above for the surface of the Earth? Okay, well, let me jump to there. Let's say that we're at this height here above the surface of the Earth, and this dotted line right here is perpendicular to the field lines themselves. Okay, notice that the spacing or the density of the field lines is the same at all points along this dotted line. What that means is that at all points along this dotted line, the strength of the gravitational field is the same. Okay, compare that to this height here, where once again this dotted line is perpendicular to the field lines themselves, like so. Notice that along that dotted line, the spacing or density of the field lines is a constant, so then therefore the gravitational field is a constant at that location. There's no difference at all, by the way, between the spacing of the field lines at this height here and the spacing of the field lines at this height here. This then means that the magnitude of the gravitational field is a constant for all points in space here, as long as you're near the surface of the Earth. Remember, however, that that's just an approximation. In terms of Newtonian gravitation, recall that the gravitational force obeys an inverse square law. So then therefore, let's say that we get very far away from the Earth, and then such that we could see the entire Earth. What does the Earth's gravitational field look like then? Okay, well, let me do some erasing here. Okay, so let's say that right here is the Earth, like so. So now we're very far away from the Earth. And let's draw the Earth's gravitational field when you're away from the Earth. I'm not going to draw the gravity field if you were inside the Earth. That's a more complicated topic. So for example, if I take a mass m and I place it right here in this location, the force of gravity exerted upon it is going to be radially inwards towards the center of the Earth. Same thing if I take the marker and I place it here of mass m, there's going to be a force of gravity exerted upon it like so, once again radially inwards towards the center of the Earth. So then therefore the gravitational field lines then have to look like this. Once again, I'm just going to draw them here outside of the Earth itself. And then symmetrically, like so. So if I take the marker and I place it anywhere in space here near the Earth itself, as long as we're very far away from the Earth in this manner, then the force of gravity exerted upon it is going to be radially inwards towards the center of the Earth. Okay, now compare two heights once again. Let's say this right here, this dotted line, and this dotted line is always perpendicular to the field lines themselves. At that dotted line, let's call this height 1. Okay, and then right here we'll say, there's another dotted line. Once again, this is a perpendicular. This right here we'll say is height 2. So which height, 1 or 2, is the Earth's gravitational field stronger? It's obviously height 1, and the reason for that is because notice that the lines are closer together here for height 1 than they are for height 2. In other words, the spacing or the density of the field lines at height 1 is greater than it is at height 2. So with no mathematics whatsoever, what we come up with here is a very powerful visual way of understanding, at least in a qualitative manner, how the Earth's gravity behaves. How the Earth's gravitational field looks then, this then determines what would happen to an object, for example, if we then placed it here in the field. So we come up with this very visual picture, very powerful picture of visualizing the Earth's gravity. By the way, I do have a poster of Michael Faraday in my classroom. Here he is when he was a relatively old man. He died in 1867. Okay, let me put this off to the side. Okay, now let's extend this idea and talk about it in terms of electric charge instead. So now this is the electric field. And let me just describe to you various types of charge configurations and electric fields associated with them, and then we'll get to the math associated with it in just a little while. Let's say, for example, first of all, we start off here with a positive point charge, so a proton, for example. Okay, what does its electric field look like? Well, by definition, we always describe the electric field associated with this charge in terms of its effect on another charge. But that other charge, by definition, is always considered to be positive. This is referred to as a positive test charge. So if I take a positive test charge and I place it right here, there's going to be a force of repulsion exerted upon it due to this positive charge here. So then therefore there would be a force in this direction like so. Okay, do the same thing elsewhere in space here. So let's say I take the positive test charge and I place it here. Once again, there's going to be a force of repulsion exerted upon it like so. So then therefore in 3 dimensions, even though of course I'm drawing this 2-dimensionally, in 3 dimensions then you end up with an electric field associated with this positive point charge that is radially away from this positive point charge. That then looks like this. Notice how I'm drawing the arrows here associated with these electric field line vectors. What this is a representation of the force that would be exerted upon a positive test charge due to this positive charge right here. So then therefore, by definition, if you're talking about a positive charge, the electric field lines are away from that positive charge. It's backwards, however, for a negative charge. Okay, so this right here, you may want to write this down in your notes, is for a positive point charge. Okay, now I'll change the situation to describe then the electric field associated with a negative point charge. Let me change that word now to negative. Like so. All right, so right here is a negative charge, and now we describe its electric field in terms of the effect that it would have on another positive test charge. So if I take a positive test charge and I place it here, there's going to be a force of attraction exerted upon it like so, due to this negative charge. Do the same thing up here, place the positive test charge here, and there's going to be a force exerted upon it like so, due to this negative charge. So then therefore you end up with an electric field that basically looks identical to the electric field associated with the positive point charge from a few minutes ago, but in this case all the field lines are radially inwards towards the negative charge. They then therefore look like this. So notice how I'm drawing the direction here of the vectors. The field lines themselves, like so. Looking like this, symmetrical, like so. So if I take a positive test charge and I place it anywhere in space around this negative point charge, this then means that there's going to be a force of attraction exerted upon it like so towards that negative point charge. Let me kind of adjust the diagram like this. Okay. Okay, now the beauty of Faraday's idea of the field is that number one, he comes up with the idea just as a means of visualizing the electric force because he had to compensate for his own lack of mathematical skill. But the beauty of his idea is that it actually physically exists. So at this point in the lecture, pause the film here and then take a look at the video that I have uploaded for you called Electric Field Demonstrations. So take a look at that first before you continue with this film. So go ahead and pause here. Okay, and now that you've seen those demonstrations, let me go ahead and continue here by once again drawing out a few more fields for various charge configurations. There are basically 3 more that are important. Okay, the first of those 3 is what is called a dipole. A dipole consists of 2 charges, one positive and one negative, that are separated from each other by some distance. So let's say that right here is a positive charge, a plus Q we'll say. Right here is a negative charge, a minus Q, like so. And then the net electric field associated with this configuration has the following shape. Drawing it symmetrically. It is 3-dimensional. And the field lines then therefore look like this. Once again, the field goes away from a positive and towards a negative, hence the direction associated with the field lines. Let me draw 2 more. Be a little bit more complete about it. Like so. The reason why a dipole configuration is so important is because it's extremely important when describing what happens when chemical reactions occur. Some types of molecules are polarized. That is, they consist of a positive charge on one half of the molecule and a negative charge on the other half of the molecule. The prime example of this would be water, H2O. The reason why water is so important when it comes to chemical reactions, the reason why chemical reactions occur so often in water, is because the water molecule itself is very highly polarized. It has an electric field that looks like this. So here's the basic description of a water molecule. For those of you that have already had a chemistry class, you're probably already familiar with this. For those of you that will to be taking chemistry later on, well, you'll remember today's lecture in light of that later on. Okay, so let's say right here is a water molecule. This is a perfect example of a dipole, which hopefully everybody is familiar as the chemical formula H2O. 2 hydrogen atoms and 1 oxygen atom. Okay, the actual shape of the water molecule itself, it kind of looks like Mickey Mouse ears. So right here is a hydrogen atom, right here is a hydrogen atom, and then right here is an oxygen atom, like so. Oxygen, hydrogen, hydrogen. Okay, the 3 atoms are bonded together by means of what is called a covalent bond. The electron shells of the 3 atoms are shared amongst the atoms themselves. Those details are talked about in the chemistry class. Covalent bond. Okay, now the mathematics of the water molecule are extremely well understood, and basically what it boils down to is the following. On the average, most of the electrons associated with this molecule spend most of their time down here on the bottom half of the molecule. So then therefore the bottom half of the molecule here, that becomes overall negatively charged. And then because most of the electrons associated with the molecule spend their time down here, this then means that this half of the molecule, where you still have protons associated with the hydrogen nuclei, well, that then becomes positively charged. So you end up then with like a splitting of the charge, if you will, from one half of the molecule to the other. In other words, the molecule is polarized, just like I polarized my conducting piece of metal in my electroscope in my charging by induction demonstration that you saw in one of my previous lectures. So the water molecule is polarized. For that reason. So mathematically then, we can represent the polarization of this water molecule as a dipole. In other words, mathematically it behaves as if there's a positive charge up here and a negative charge down here. And then overall, the electric field shape associated with this dipole is exactly like what I drew a little while ago. Okay, here's, by the way, a short demonstration. I just thought of it, so I'm going to go ahead and get some equipment here of the polarization of the water molecule and its strong electric field. If you need to, just go ahead and pause right here while I go ahead and get a couple of pieces of equipment. Okay, so I'm going to go ahead and start my faucet here at my sink at my desk. This is the only time that I ever turn this faucet on, by the way, is for this demonstration. And then I get a stream of water like so. Okay, and then here's my plastic rod and my rabbit fur, so I'm going to go ahead and charge this up. So when I charge this up, then this then becomes positively charged. And then a force will be exerted upon the stream of water due to the positive charge, for example, that is placed fairly close to it, like this, like so. So you can see that the stream of water here is being attracted to the positively charged plastic rod, like so. And one of the reasons why this is because the water molecules themselves are very highly polarized. They have an electric field associated with it, okay? All right, I'm gonna go ahead and put this away now, so go ahead and pause if you would like. Okay, the next electric field configuration that's important has to do with what is called a line of charge. A perfect example of a line of charge would just be a wire. So what I'm going to do on the board is draw the wire as if it's pointing out at us like this. So now this is a line of charge, a wire, and this is a nice example. And let's say that here's the wire like so, basically pointing out at a board at us. I'm drawing it on an angle like this. It's coming out at us like this. Okay, at all points along the wire itself, the electric field lines are perpendicular to the wire and they are radially outwards from the wire. So for example, let's say that I take a look at this point right here on the wire. At that point right there, the electric field lines look like this. We'll think of the wire, by the way, as positively charged for simplicity, like so. So all of those electric field lines are perpendicular to the purple line and they are radially outwards from the purple line. Same thing at all points in space along the wire itself. So for example, right here at this point, perpendicular to the purple line for the wire, you would have the electric field lines like so. And then one more point, say right here, once again perpendicular to the purple wire, like so, you would have electric field lines that look like this. Okay, I use an applet in my screencast lecture in the folder from today to show you the electric field associated with these charge configurations as I'm lecturing here. If you want to pause the film right here and go to that screencast, I invite you to do so. I also posted a link to the applet that I was using during that screencast. Okay, and then lastly, once again, when it comes to important charge configurations here, the electric fields associated with them, what is referred to as the infinite sheet. Okay, now when I say infinite sheet here, what I mean is an infinite sheet of charge. It's usually drawn like this. It's infinite in extent in this direction, and it's infinite in extent in this direction, like so. In other words, the infinite sheet of charge looks very similar to what the Earth's surface looks like when you're standing on the surface of the Earth. When you're standing on the surface of the Earth, it kind of looks like you're standing in the middle of an infinite sheet. Now recall from earlier in the lecture that the Earth's gravitational field is a constant and it's straight downwards, and at all points in space, the gravity field itself is a constant. Remember, however, that's just an approximation. The Earth, of course, is spherical. So then, therefore, by analogy, if you have an infinite sheet of charge, you end up with a constant electric field that basically points away from the sheet if it's positively charged, or towards the sheet if it's negatively charged. So let me think of this as a negative charge, just for simplicity, so we can make a comparison between the gravity field associated with the Earth when you're near its surface and this charge configuration. All right, so now the electric field is going to be a constant. Draw it like this here initially above the sheet, and it looks very similar, as I said, to the Earth's gravity field when you're near the surface of the Earth. But we also have this region of space here down below the sheet as well for this configuration. So then therefore the electric field lines are towards the sheet like so, down here at the bottom. Okay, you can see these electric field lines also in that little applet in that screencast video that I mentioned earlier. Okay, I'm going to go ahead and pause here and call this part 1 of the lecture. There will be a part 2 of the lecture where we'll take a look at a couple of example problems as well.